be substituted with that, right? It's a material stiffness. What is U prime?
Strain.
Yep. And what does the L mean? We're talking about strain where? At the end of our beam or at the end? So this, all this is right? Sigma is equal to EE at X equal to L. So at the end of the beam. So let's just get to remind ourselves what this stuff means. So that's our strong form. Our weak form, which we've shown in a convoluted way, that is equivalent, is find our displacement field, U, contained in our delta. So we have our bilinear functional, UW is equal to LW. For all contained in this subspace V, on EV, where our bilinear functional is equal to the integral from 0 to L E A U prime W dx, and L of W was equal to 0 to L B W dx plus sigma AL UL. Okay, so let's just remind ourselves of that. So we have that at the top of our notes. That's what we're trying to solve. And we'll remind ourselves of our simple beam. And we have a stress, and L is that distance. And finite element method in 1D, one dimension, we have a domain, omega, which is equal to 0 to L. And let's go. We need to discretize omega into elements. In omega such that omega is equal to the union of this omega subset E, where E is equal to 1. So that just means all of what this means is we have to discretize the whole thing. So all this is saying is we have a 1D element. We have, we want to look at this one dimensional, and we need to split this up into bread slices. We have to discretize it. And we're going to evaluate this in different elements where these little guys are called elements. And we have to do that over the whole 0 to L. Okay. And excuse me. Not a variable. if I ever use it. I'll write it down in case we do. I don't see it. So we're going to define this variable m. And we're going to say that this is the num_l. So if you were programming this, like if you were to look like at Abacus code or an ANSYS code or something like that, you're going to use this m as a variable, and it's going to refer to this num_l, and that means number of elements. And so essentially what we have in this beam that I drew up here is we're going to represent that beam as almost like a number line. We're one-dimensional, so we have x equals to 0 and x equals to L. And we're going to break this up into 1, 2, 3. And I'm going to call this 1, 2, 3, 4. And the number in a circle is the element. Element E. So we have 4 elements. So let me put a bullet next to this one. So the next one is for each element, we discretize it into NEL, which is the number of nodes. So NEL is equal to 2, 3, and this is number of nodes per element. So for example, NEL equals 2. So we have one element, E, and it has 2 nodes. Node at each end. Or, uh-oh. Did you guys see that pop up?
Yeah.
Yeah.
Bad news. Let's call this E1, E2. So we have 2 elements. One, or actually, sorry, this is one element, E, the whole thing, and we have NEL equals to 3. So it's one element represented with 3 nodes. So far, so good?
Yeah, I'm following.
Okay. It seems like overly simplistic, like, yeah, why are you doing this? Until we actually get into, we start adding the crazy variables in math, and it's like, what the heck is going on here? So let's do another one where we have, let's count them, 1, 2, 3, 4, 5, and So we're going to number this one 1, 2, 3, 4. So in this particular example, num_L, number of elements, equals 4. And our, we're going to say n is equal to total number of nodes is equal to 5. What does nel equal?
2.
Right. We have 2 nodes per element, right? So we have 4 elements. We have 2 nodes per element, but in what's shown right here, we have a total of 5 nodes, and this would actually continue. This could continue. So what we're seeing here is these nodes are labeled in a global sense. Can you see that you could write this? So what we have shown here is we have 4 elements, 1, 2, 3, 4. Each one of these has 2 nodes, but can you visualize that there's like a local coordinate system here for this one element? It's actually, I don't know if this will show up. Maybe we can call this like 1A and 1B. But this node right here could also be represented by 2A and 2B. Can you see that they would have, the nodes would have a local, they could have a local numbering relative to the element that they belong to?
Yeah.
From a global perspective, it would just be 1, 2, 3, 4, 5. There's the total. Okay. Is everybody good with that?
Yeah.
Okay. It's
And
kind
just to be clear, so like NEL is basically just denoting how many nodes there are per each element.
Yes. 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 And this kind of goes back to it's essentially what we're going to be doing. Remember, we started off the semester, we were talking about coordinate transformation, and we were going from a local coordinate system to a global coordinate system. That's exactly what we're going to be doing here, where we have to take the things going on at the element level, and let me take it back. Things going on at the nodal level and relate it to the element. And then things going on at the element, we're going to do some calculations, not, at the element level. And then we have to take the result of those and we have to do coordinate transformation to get back to a global coordinate system. So it's about creating relationships. Okay. So stick with me. The boringness is not over yet.
That's like an inception of FEM.
Yeah. Now we're going to convolute things. Of course, right? We're not going to keep this simple. We're going to associate a course basis function. We're going to call this, make sure I get this variable correct. We're going to call it phi A. That is a horrible phi. Yeah, not any better. Phi I of x. So remember, we're still talking about 1D. We're keeping this simplified to one-dimensional right now. So we're going to associate a basis function, phi of x, to each node. And I'm just going to call that I because we could have however many. And to contrast, it's probably not a right way to write that. Let's say this phi of x uses the notion of mapping from a local relevant element to the physical element. And we're going to call this omega E. So omega E is referring to the domain of our element. So if we come back here to our example right here, and we're saying that this 1 to 5 is x equals 0, x equals L, from 0 to L. This is omega. This is our domain, 0 to L, right? 1 to 5. Elements 1 to 5, or nodes 1 to 5, I'm sorry. Nodes 1 to 5 is our domain. Can you see that we have a omega 1 and omega 2 element, an omega 3 element, omega 4 element? So this subscript is referring to just our element from node 1A to 1B. That's omega 1. And 2A to 2B is omega 2. So we're talking about a subset of our part, right? These are the slices of the bread. These are we're discretizing this. We're splitting it up. So we're talking about a subdomain, omega E. And of course, it's going to be convoluted. We're going to take our element and say that this is E, so it's some number. And this is E plus 1. This is our element. These are our node numbers. We're just referring it to E and E plus 1. This is our x-axis. And we're going to map it to this new domain that's represented from -1 to 1. And we need to come up with a way to map back and forth. Mapping. It can go both ways. And when we're in this domain over here, that is, we're no longer in the X domain. We are in the I always write this guy strange. It's XI, it's C. So that's the Greek letter or the lowercase XI or C. So we're mapping from these nodal values, which from our example up above, this could be element 1. And remember, I wrote 1A and 1B. We're mapping. So this is in omega 1 and omega 1 domain and in X space. We're mapping to this new coordinate system, which exists from -1 to 1. And we're in this, we're still in this, this omega 1 space, if you will. But a lot of times it's referred to omega naught. It's the same essential space, and in its in this C space. So we're mapping our elements and essentially our nodal values, our nodal numbers, to this C space to do stuff at the local level, to calculate things, and then we're going to have to map it back to the global level when we're all said and done. Does that somewhat make sense? So this C space is the reference of the system where we define the Lagrange polynomials or for people that do FEA stuff and you're reading the help files, these are called shape functions. So let our UH of E in our C space be the displacement interpolant in omega naught. So this is our sub omega space that has been mapped. Where omega naught exists from -1 to 1 in the C coordinate system. Is everybody okay so far?
Yeah.
It's very abstract, isn't it?
This part got a little bit more abstract.
Okay, it's gonna get worse.
Is the U with the H superscript, is that H superscript the continuity of it, or what's the H superscript there?
No, that was the, if you go back to, I think last time or the time before that, where we did weight functions, it's that, that it's a displacement to the H. That's where we brought in the Rayleigh-Ritz example. So that's part of the Rayleigh-Ritz application. Remember, it was U. So Rayleigh-Ritz was U of H of X was equal to the sum of I is equal to 1 to n, this phi j x cj, which was a trial solution. You remember that?
Yeah, that's right. Okay.
Okay.
And
So
it says displacement interpolant, or
yeah, so this is this U of H, this displacement field right here, this trial solution. This is a trial solution for, in this particular case, is a displacement field. But now what we're talking about is a displacement field at the element in the C space. So we're mapping this trial solution into the C space at the elemental level.
okay.
So I'm going to box this because it's kind of an aside for this topic. So start. Like I said, what we're going to do today is not really applied, but it kind of is. Start with nel equals to 2. Okay, so we're talking about a single element, 2 nodes. So let's our UE of H C equal N1 C U1 plus N2 C U2, where N, I'm going to put this nomen numeral I, so it's representing these indexes 1, 2 of C are linear, Lagrange, shape functions. With the following properties. So first and foremost, we're going to write out our element. And we always write out like this. So we're talking about we're in our C space. This is C is equal to -1. C is equal to 1. And I'm just going to write this as node 1, node 2, so we can kind of keep track of things. And the way this works is n sub I c j, oops, this is c of j equals, this is the Kronecker delta, I, so remember the, so remember Kronecker delta was if these two indices are the same. So if I is equal to j, then our Kronecker delta was equal to, remember what that was?
Zero.
If they're equal, it's equal to 1. And if I does not equal j, it was equal to 0. So what this is saying is that our NICJ is either going to be 1 or 0. So what happens is we have N1 at -1. So this guy right here, C is equal to -1, is equal to 1. And N1 of 1 is equal to 0. N2 -1 is equal to 0. And N2 of 1 is equal to 1. So if we go to our little line here, where we're C space, we're at -1 and we're at 1. And this is our C space. What we're saying is that the amplitude, the value at -1 here is 1. And at n equals to 1, it's 0. So our shape function shoots up to 1 and comes down. So that's our first shape function. At -1, it's here. Oh, actually, it's, you don't really have this line here. So that's one shape function. The other shape function goes from -1 to 1. Okay. So N1 C is equal to 1 plus C over 2. And N2 of C is equal to 1 plus C over 2. These N1, N2 of C, these guys right here are our shape functions for this element. So this is how we go from -1 to 1. So as we go from this element or from this node at C equals -1, as we travel in the positive C direction, this Lagrange function is going to go from 0 to max out at 1. And the other shape function is going to start out at 1. And as we go from -1 to 1, it's going to go to 0. So note that
Isn't this a negative on one of those definitions? They're the same, it looks like, unless I'm missing something.
no, because this one right here is actually 1/2 plus c over 2. It's not in parentheses. Hold on. Let me double check. N1 is C. Actually, I think.
The negative would give a slope to one of them.
Yeah.
Or opposite slope.
I think what it is this one is negative. Yeah, it's negative. And one is 1 minus c over 2, and the other one is 1 plus c over 2. But it changes. So so note that N1 C plus N2 C equals 1. And this implies this: the sum of I is equal to 1 to nil N I of C is equal to 1. And this is called partition of unity. I've seen error codes in ANSYS that refer to this. When I've seen it, I don't know what was causing it, but it's basically meaning that they're not able to map from a global coordinate system to a local coordinate system for whatever reason. It's not able to do this for a particular element or an element type. So here's another one. Let's look at if nel is equal to 3. So we have a single element. Those are supposed to be evenly spaced. So this is one element. And we have, I'm going to say C1 is equal to -1. -1. And remember, it has to go from -1 to 1. So I'm going to say this is C3, this is equal to 1. In the middle is equal to 0. So these shape functions end up looking different because we have to go from the value of 1 at -1 to 0 at 1. So what happens is your first shape function, try to get this right. Your N1 of C, first shape function, it starts at 1 and it linear decreases from -1 to 0. And then it goes negative in a nonlinear way and curves back to 1. And then you've got another one that goes the other way. So it linearly goes from 1 to 0, and then comes back to -1. And then you have another one that just goes from -1 to 1, so 0 to 0, and it's 1 in the middle. In this particular case, for shape function is n1 of c is equal to c times 1 minus c over -2, which simplifies to c over c minus 1 over 2. And we have an n2 of c is equal to 1 minus c squared, and n3 c is equal to c1 plus c over 2. And again, these are called Lagrange shape functions. So what we're ultimately trying to get to with this is we have, let's do a little aside here, just for giggles. We have a potato, and we're discretizing this. And you know, these blocks here are elements. And in these particular potato, I have 1, 2, 3, 4. So I have 4 elements here. Or sorry, 1 element, 4 nodes. And what we've said is that when we want to break this out, this little element, we want to break it out, and we want to look at this kind of all by itself. And when we're over here, we're going to call this X space. And when we're over here, we're going to call this C space. Right? And when we're over here, I might have, maybe this is element 11, 15, 18, 23, right? I'm going to have some nodal elements. But when I'm over here, things have to be like 0 to 1. And ultimately, we're going to have to figure out how we're going to do that. Let's say that our coordinate system is splitting this like this. So I would be -1, 1 down here. So if this is 1, then that would have to be a -1 and a 1 over here. So we have to do this weird mapping, right? So we're trying to take this sub piece out of our part and map it over into this other space. And we're saying that, okay, when we do this mapping, the values at these different 1 and -1s, they have to be our trial solution. It either has to be 1 or 0. That's all we're saying. We're going to make a guess at our trial solution, and either that trial solution is you either have the whole thing or you have nothing. That's all we're saying right now. You're not going to have a portion of your solution, or because we're evaluating it. At this particular case, we're evaluating it at the nodes. We haven't got into anything in between. We're evaluating at the nodes right now. So for this is more notation, for our nel equals 2, we have UEH C. So remember, this is the Raleigh-Ritz trial solution in C space now is equal to N1 C U1 plus N2 C U2. But we defined what N1 and N2 was. Actually, yeah. We defined N1 and N2 right here. So we can plug in, if we wanted to, we can say this is equal to um, 1 minus C over 2 UI or U1 plus R1 plus C over 2 U2, right? We just plug in our value for that. So we end up getting a UEH when C is equal to C1. That leads to U1. So this is when this equals -1. And we have a UE of H C equals to C2 is equal to U2. And this is when it equals +1. Where UI, so U1 and U2, are nodal displacements. Okay, so I'm going to write this out. Previous example, 1, 2, 3, 5. Kind of start thinking about things. Element 1, element 2, element 3, element 4. We have node 1, 2, 3, 4, 5. So we have element and we have nodes. And I'm really just writing this out so you can start thinking about this in matrices or lists and things like that. So element 1 is associated with nodes 1 and 2. Element 2 is associated with elements 2 and 3. Element 3 is associated with elements 3 and 4. And element 4 is associated with nodes 4 and 5. Okay. So we want to start thinking about trying to keep things organized like this. Now, ultimately, what we're doing is called isoparametric mapping, where x sub z is equal to the sum of I equals to 1 to null and I c x I to the e, where x I to the e are nodal coordinates. So we're in X space, we're in C space. This is E plus 1. Our domain is omega E. And we're going to call this x1E, x2E. And here, we're going to call this 1, and this 2, and this is C equals minus 1. This is C1, and we have C2 is equal to plus 1. And the idea of going from, choose different colors, going from E to 1, that maps there. It can map back and forth. Our E plus 1 maps over to our C2. We can map back and forth. But also our element maps. So we're mapping 3 different things. We're mapping our node, or actually it's 2 things, elements and nodes, is what we're mapping from a X coordinate system to a C coordinate system. So maybe we can go back up to this guy right here, this 1 to 5. So I think I wrote this earlier tonight, but this is domain 1, domain 2, domain 3, domain 4. So it's 4 domains. So we want to think of the element as a domain. Okay, so we have Lagrange shape functions, or Lagrangian shape functions. And remember, for the simple solution, it was just NIC is equal to 1 minus C over 2, and 2 of C is equal to 1 plus C over 2. So those are our Lagrange shape functions. Depending on how many nodes that we have, they get really complex. And now I've created this relationship with X. So we're saying that X is equal to 1 minus C over 2. X1 of E plus 1 plus C over 2. Actually, we should put these in parentheses. X2 of E. So this is really just defining our total X length and a function of our of our Lagrangian. Now, let's go back up. So remember, we kind of started this chaos with talking about this Rayleigh-Ritz and this trial solution, right? So how all of this is going to play into each other is basically this guy right here, this phi. Phi is this character that is part of our trial solution, which is going to include some of this mapping. So keep that Rayleigh-Ritz idea in your head. And we want to think of this phi I of X such that the local restriction of phi I of X to an element in Ni C of X. So we're going to take our shape function and we're going to merge it with this idea of a trial solution. And essentially what we get so let's say that this is node 1, 2, 3, 4, 5. We're in the X domain. What you're going to get is these trial solutions. So let's say we have phi1 of X starts off here, phi1 of X, and we're saying at 1, it's equal to 1. So this is, a vertical height of 1. So the value of it's 1. It's 1 here, and then at 2, it's going to be 0, and it stays 0 everywhere else. And then for let's say for phi2, we have something that looks like it's going to go from 0 to 1. So this is phi2 of x is 1. And then it's going to drop back to 0 and it's going to stay 0. And so on. So then the next one's going to come along and it's going to be from here, it's going to be 0 and it's going to shoot up to 1. And then it's going to come back down to 0, be 0. And it would be 0 from the beginning, from 1 to 2, shoot up to 1, back down. And then, so phi I are called finite element basis functions, if you remember. And they're a trial solution. And what we're trying to say are that those trial solutions are either, they're not necessarily 1 or 0, but you either get the trial solution is either valid or it's not. So we're going to be merging these basis functions or trial solutions based on this Rayleigh-Ritz method. So Rayleigh-Ritz method uses this basis function, and we've now set to give us a trial displacement solution for each node. I should write that again. Or Rayleigh-Ritz, oh, we're almost out of time, was UH of X is equal to the sum of I is equal to 1 to N, and phi J X CJ, remember? We started with this whole thing, and that led us down this path where we ended up with Kij Cj was equal to F. So this basis function right here, what we're saying is either 1 or 0, depending on what node we're on. So because we're talking about elements and mapping and nodal values, is right, yeah. We now have U, E, H in the C space is equal to the sum of this I is equal to 1 to Nell, B, J, C, and this would be a C, J. So this basis function that we're going to plug in here helps us with this trial solution. And if you remember from differential equations, a trial solution is just an educated guess, right? It's something that we pick that we know is going to give us a solution to the boundary value problem. You kind of remember that at a very high level concept. It's something that we're pretty darn sure it's going to work. So this trial solution we know is going to give us a solution to, it's going to give us a displacement field that works without any discontinuities in it. That's C0 continuous. And what we're trying to hone in on are what are these fees? What are these basis functions that we're trying to come up with? And what we're saying right here is, okay, that basis function either exists at the node or it doesn't. You either get all the basis function or you don't, for each one of those nodes within a particular element. And oh, by the way, that basis function is called these Lagrangian shaped functions that we're going to be utilizing. So we'll create some relationships there. It has to do with mapping. So, okay. So next time, I think I may have, yeah, I do. We'll start to make a little bit more sense of this, in that we'll merge this whole lecture together with the problem that we started out with. Well, actually the weak form. So we'll see how this stuff gets plugged into there and how we start developing our matrices that we have to solve using a computer, or at least getting closer to it. Okay. So have a good night. We always run over. I'm really sorry about that.